What if a mathematical proof wasn't just a list of logical steps? What if it was actually a shape? Sounds a little out there, right? Well, today we're diving into Homotopy Type Theory, a field that's building this wild, totally unexpected bridge between the abstract rules of logic and, well, the physical intuition of geometry.
So here's our game plan. We're going to start with the logical bedrock, type theory, before we cross that bridge into the world of shapes. Then we'll get to the key that unlocks the whole thing. It's called the Univalence Axiom, and see how computers are using these ideas to build literally flawless proofs. Finally, we'll ask the big questions. Is this a whole new foundation for math, and what does that even mean for the future of truth itself?
All right, so where does all this begin? Before we can even start talking about shapes, we have to get a handle on the language of logic they're built on, and that language is type theory.
It sounds like the simplest question in the world, doesn't it? But really stop and think about it for a second. What does it actually mean for two things to be the same? For example, is the expression 2 plus 2 truly identical to the number 4? Or are they just two different ways of getting to the same value? That little distinction, it turns out, it's everything here.
This is where type theory comes in. You can think of it like a super strict grammar, but for math and logic. You know how regular grammar says you can't add a noun to a verb? It just makes no sense. Well, type theory says you can't just add a number to a shape. Every object has to belong to a type, and there are these incredibly precise rules for how they can interact. And that rigidity, which was pioneered by thinkers like Martin Loaf, is exactly what makes it so powerful for both super abstract logic and very practical computer code.
Okay. So that logical grammar is powerful, for sure, but it's still pretty abstract. So what happens when we ask a really radical question? What if these types actually had a shape?
And that brings us to Homotopy Type Theory, or HoTT for short. It takes that rigid system of logic and suggests something kind of mind-bending. Let's interpret every type as a space. So a collection of numbers isn't just a list anymore, it's a line. A logical statement isn't just true or false, it's a landscape. All of a sudden, these abstract rules gain this physical intuition you can almost, reach out and touch.
And here it is. This is the core analogy that makes the whole thing just click into place. A type is a space. Picture a sphere. An element of that type, something we call a term, that's just a point on that sphere. So what's a proof that 2 points are equal? Well, it's a path connecting them. Just like that, logic becomes geometry. This is the absolute heart of the idea.
And this completely changes what equality even means. In traditional math, equality is like a simple light switch. It's either on or off. Two things are the same or they're not. That's it. But in HoTT, equality is dynamic. I mean, think about it. There can be multiple paths between 2 points on a globe, right? Well, in the same way, there can be multiple proofs that two things are equal. And each of those proofs, each path, has its own unique structure. Sameness is no longer just a fact. It's a relationship.
So, we have this really beautiful bridge between logic and shapes, but what actually makes it strong enough to use? It all comes down to one powerful central rule, the Univalence Axiom.
This whole idea was really championed by the Fields medalist Vladimir Voevodsky. His goal wasn't just to explore some cool new idea. He wanted to rebuild all of mathematics from the ground up with his Univalent Foundations program. Identity is equivalent to equivalence. This simple little phrase is the philosophical core of it all. What it means is that if two mathematical structures behave in exactly the same way, if they're equivalent, then we can just stop treating them like they're lookalikes and declare them to be truly, fundamentally identical.
The Univalence Axiom is what turns that philosophy into a formal law. It's the engine that drives the entire system. It basically gives us permission to swap out any structure for an equivalent one, and we know that the mathematical truth is still going to hold.
Now, this isn't just some beautiful theory to admire from afar, it's a practical tool, and its biggest impact right now is happening in the world of computer-assisted proof.
Because type theory is so grammatically precise, it's the perfect language for computers to understand. And HoTT is now the foundation for a whole new generation of proof assistants. This is powerful software that lets mathematicians and programmers verify with absolute certainty that their super complex proofs and critical software are 100% correct. Tools with names like Coq, Agda, and Lean are these proof assistants that have been used to formalize some of the most complicated theorems in all of mathematics. They're built on the principles of type theory, and more, they're incorporating the insights of HoTT to become even more powerful and honestly more intuitive.
Okay, so if this theory is powerful enough to check proofs, could it be powerful enough to do more?
I mean, could it form a whole new foundation for math itself?
Well, that is precisely the goal of the Univalent Foundations project. For more than a century, pretty much all of math has been built on one single idea, the set, which is just a collection of things. This project is proposing a radical alternative. It's asking, what if we rebuilt everything, from the ground up, using the more intuitive ideas of shapes and paths as our fundamental building blocks?
Just think about that paradigm shift for a second. The old metaphor was like building with bricks, simple, identical sets. The new metaphor is more like building with maps and landscapes. And in a world that's made of shapes, the idea that two equivalent things are the same isn't some extra rule you have to tack on, it's just a natural, obvious feature of the terrain.
Wow, we've journeyed from pure logic all the way to dynamic shapes. So where is all this heading? What does it really mean for the future of proof itself?
If there's one thing to take away, it's this. Homotopy Type Theory gives shape to pure reason. It transforms the flat, black and white world of logic into a dynamic geometry, a world where ideas aren't just statements, but spaces filled with paths and connections and all sorts of hidden dimensions.
And this leaves us right on the edge of a new intellectual continent. A proof is no longer just a sequence of steps. It's a tangible object with its own unique geometry. And that leads to the ultimate question for the future of mathematics. What else can we understand once we see that a proof has a shape?